Boulder, what,
30 years.
Like 2 days together. There was very enough metaphysics here, certainly theory, 1995, July 1995, and then we actually knew each other through our wives, but didn't know there were. CU made 2 offers, one to Dan and one to me, but we didn't know of each other that each of us were coming to Boulder, and then we're pleasantly or unpleasantly surprised. Our offices were right next to each other.
I escaped one door down later.
Anyway, so Dan is a photo emission expert, and he's going to tell you all about photo emission today. So take it away, Dan.
Yeah.
Thank you.
Pleasure to be here in Boulder for the last 30 years. And I just realized how crappy this image is. Yeah, hoping the rest of my slides are a little resolution than this one, but you've seen this view many times now. You're here for 3 weeks. I would say just the bad in comparison to the vast majority of these lectures, which really were dominated by, Blackboard work. I'm almost exclusively going to use the projector because there's real data, the real experimental data. I could try to sketch it on the board for you guys and hide whatever defects or make things look prettier, but that's just not fair, right? So there's going to be a lot of real data that I'm showing, and that really requires this. And ARPES, Ang-Resolved Photo Emission Spectroscopy, correlated electrons. That's what we're here for. So just very briefly, ARPES, of course, is for measurements of the band structures, energy versus K, Fermi surfaces, orbital symmetries, etc. Particularly important for correlated electron systems, where band theory, which much of our community uses to access the E versus K relations, often has limited applicability, at least needs to be modified, renormalized, etc. Okay, so here we can directly measure these. Also very important are the self-energy effects, the many-body interactions. We can get those as a function of K and T. I'll spend a lot of time on that. I know that's really central to this whole workshop. That's really where I'm going to get the dynamics from for the title of this entire summer school, is from these self-energy effects. And so I'll spend a lot of time on that. We can also, of course, measure superconducting gaps, pseudogaps, etc., spin of the electrons, orbital natures of the electrons. Pump probe ARPES is another way to access the dynamics. Margaret Manan gave some talks. I think she covered that much, in detail. I will not be focusing on this because she did that. Also, my own bias is that still, even though there's huge advances here in this pump probe ARPES, at least to date, the regular ARPES, even for the dynamics, has been more influential. Okay. Compared to other spectroscopies, of course, the K resolution is really unique. We can get K resolution for momentum transfer, neutron scattering, etc. That's a Q, a moment transfer. This is individual Ks. And so with energy and K, this is arguably the most direct of the spectroscopies for the electronic structure. It is surface sensitive. I will talk more about that. I think all of you have heard that. I'll talk about why that is, but it definitely requires high quality surfaces if we want to access the bulk physics effects. For studying a topological insulator, and we're really interested in surface effects, this is brilliant. This is absolutely what we want, and ARPES has made amazing advances for that field of topology and these special surface states. For most of what I'll be talking about here, that surface sensitivity is a disadvantage because I'm really aiming for the bulk physics. Energy resolution is continually improving. We're now, typically 1 to 10s of millivolts scale Not as good yet, for example, as the very best tunneling spectroscopies, but continually improving. And the same goes with base temperatures. Spatially, we're typically something like 10 microns or up. So again, not at all in the regime of STM, but continually improving. And there are a few efforts now with nano ARPES where on the scale of 100 meters is even possible. And definitely people are interested to push that. We only measure the occupied states, although pump probe, ultrafast pump probe ARPES, now can access some of the unoccupied states. And again, I won't really be focusing on that. Okay, so that's very brief over many more. So let me move forward. Interrupt at any time? Good. Okay. So I'm going to begin with a discussion of the technique. I'm going to cover a number of case studies. I'm going to do a lot of focus on hoop rates. There have already been so many nice talks on that with strange metal physics, et cetera. And so I, in choosing, felt this would fit nicely, would connect well with those many other talks. It's also something that's very dear to my heart. Okay, I'll focus on studies where ARPES has made the largest initial impacts, partly historical in nature. And much of what early studies focus on was peak tracking, again, E versus K type things. But now, more and more, people are focusing on self-energies, and I will really talk about that. So evolution of electronic structure from the parent Mott state, Fermi surfaces, gaps, self-energy effects. Those are kinds of things. And now really back to the basics. Okay, for photoemission, photon in, hits your sample, ejects an electron. And here's the energy scheme for this. There's some occupied density states up to the chemical potential or the Fermi energy. The photons come in, all the energy, the photon is converted, kicked up to higher energy. If the final energy up here is larger than a value, I could have labeled this as the vacuum level. This is the work function between the vacuum level and the Fermi level. Then the electron can escape. Okay, it can escape that surface potential term, the work function, which is here. You guys all know this from Einstein. Okay, so it can escape that. There's going to be some mapping that to zeroth order in gray should exactly match this initial density of states. I've drawn it on top of some background that I show in green. So those backgrounds, I guess I've already labeled what they're from, these secondary electrons versus the primary electrons. So these primary electrons are the ones we really are interested in. They convey the information. They are not scattering on the way out. So they're the ones that give us information electron spectral function. And there's some inelastic background, typically growing in intensity the farther down you go. Okay, so you can electron on its way out on, and basically this is coming on the way out. I'll talk more about that, but electrons are scattering and they scatter inelastically, lose energy, change momentum, etc. Okay. Questions at all? Okay, very basic here. If we do it in an angle resolved way, we're not just talking density of states anymore. Now there's the energy and momentum. So the momentum of electron, the K, it's a vector. So we need to know the angle that the electrons are leaving the sample surface from. And it's just kinematics after that. And I'll show details of that. But yeah, here there's schematically drawing a peak marching towards the Fermi level, E versus K. And when it crosses, then there's our KF, the peak loses spectral intensity, et cetera. Okay. So that's very straightforward. This is why we call it ARPES, angle resolved photoemission, because we want to track the angle or the momentum of the ejected photoelectrons. Okay, for this crowd, most of you are familiar with many-body physics and the concepts of the Green's functions, the propagators, and the spectral functions, the self-energies. And so this is really what we're measuring with ARPES. The so-called spectral function A of k omega. It's the imaginary part of the propagator, or Green's function, the single particle propagator. And this is basically a Lorentzian, would be a Lorentzian term. It has a width, sigma double prime. It has a pole, okay? And you guys are all familiar with Lorentzian terms. There's the two terms here, the width, sigma double prime, of the self-energy. So the self-energy is imaginary, sigma prime plus I sigma double prime has the real and imaginary parts. The imaginary part basically tells us the width of the peak, and the real part renormalizes the dispersion. The pole that would have been, if it was a pole, if the Lorentzian was infinitely sharp, would be at omega equals ek, and now it's shifted by sigma prime, okay, by the real part. And I think this is nothing new to you guys. Now, of course, this is a causal function. The real and imaginary parts, because they're causally related, must be related through the Kramers-Kronig relations. And those are the same relations that are responsible for optics, et cetera. So Peter's talk, Peter Armitage's talk, he derived this in detail, okay? And I am not going to rederive. It's exactly the same as what Peter derived. Yes?
So from this formula, there shouldn't be a 1 over pi from, you follow the definition from first.
Okay. Okay. So let's see. Of course, the self-energy, this has the details of the electronic interactions that, or the correlations that, again, are the topic of the entire month here for the summer school. Okay, so we can access by really studying the spectral function. In other words, the widths. I'm showing you schematically here, the widths of these peaks are broadening, for example. As the peak moves away from the Fermi level, the peak is broadening. It's going to broaden both an energy or K. It's a function of energy and momentum. To 0th order, we expect this broadening, for example, from phase space arguments. If this was a Landau Fermi liquid, we inject a hole here or pull the electron out from here. There's a lot more phase space for scattering events for the deep electron than if we injected it here. Okay, for the deep hole, then injecting a hole here. Here, there's much shorter phase space, and I think I don't need to say too much more for your group. So I'm showing that as the widths. Another comment, this would be a perfect Lorentzian if sigma double prime was not energy dependent. Okay, then it is the true formula for a Lorentzian. If we go to the simplest case of a Landau Fermi liquid, we all know what the omega dependence of a self-energy should be. Anyone just want to? That's omega squared. That's right. For the Fermi liquid, it's omega squared or T squared. So already we expect this is omega squared. In other words, these would be Lorentzians because it's not constant. Multiple groups are working to develop ARPES as a real spectroscopy of this, really trying to get at these details. My own group included. And with it, we're really working to connect directly to transport, to optics, to thermodynamics, et cetera. Okay, and this is sort of the dream because this spectroscopy is more direct on E versus K, et cetera, compared to the typical transport experiment where many more things are hidden. Okay, questions? Great. Okay, how do we do it? I've shown pictures before with this thing. This is our detector. Internally, it looks like something like this. There's two hemispheres inside, two hemispherical electrodes. Here's the sample. There's an electron that photon in, electrons are coming out. There's some fancy sorting going on here for different emission angles, are eventually converted to different positions. But really the first thing is that the electrons are deflected around. You put a little more positive potential here, a little more negative potential here, and that's going to deflect the electrons around. It's a 1/r potential, like the gravitational potential around our Earth. So these are basically great circles. But the slightly slower electrons are going to be come here, the slightly faster electrons here. So this is energy dispersion. And then if we have a two-dimensional detector, which most of us use now, and this direction is angle, you can see different angles are showing up here. So we, with modern spectrometers, are directly measuring slices in 2 dimensions at the output of our detector. So we're tracking and detecting individual electrons. Okay. Electron spin detection can be added after the hemisphere over here if you want to do spin ARPES. Typically, you're suffering some few orders of magnitude in detection efficiency. So if you don't need the spin resolution, you don't want to do it in your experiment. But it's beautiful when you need it. Okay, and there's a number of facilities around the world for that. Time of flight is an equivalent way to do this if you have a pulsed photon source. And you know the time the photon hits the sample, you can measure the time it takes. The fast electron gets there before the slow electron gets there. In other words, the high kinetic energy electron gets before the low kinetic energy electron. So we can sort energies that way. Of course, you need the temporally pulsed light source. And so it's a great option. I'd say these hemispheres are still dominant in the field, but both are great. So what you have here is their electron lenses are a great analogy to optics lenses. And what they typically are, there's multiple cylinders held at different voltages. And then there's fringing electric fields between each of the gaps. And that focuses the electrons. You can see them taking different paths, retards or accelerates the electrons. Quite sophisticated actually. Doesn't work as perfectly as lenses for photons. And that's a lot of the trick. Yes?
What's physically the size of the setup?
Okay, so the typical instrument used in the lab, the radius here of this guy is 200 millimeters. So then that whole thing inside the vacuum case is something like this. And let's see, I can show you a picture. I'll show you a picture soon of the one directly upstairs. And anyone who's interested in a lab tour can come take a look at one of these beasts. Bigger than this because everything is in ultra high vacuum, et cetera, and that complicates things. Okay, let's see. Anything different here? Okay, so I guess I mentioned about the time of flight already, but with a temporally pulsed light source, pump probe measurements can be performed either with the hemisphere or the time of flight analyzer. So we're going to pump typically in the infrared or even terahertz. That's going to excite the electron, but not out of the sample. And then there's a second probe pulse that ejects it. That's in the UV or soft X-ray with enough photon energy to eject it. Here's just a schematic of what's in our lab upstairs. There's one big Ti-sapphire ultrafast laser. But ultimately what hits the sample, there's a pump pulse and a probe pulse. So something infrared, something UV, and there's this arm, a mirror, mirror, and two mirrors, and this whole stage moves. It moves physically, so now this path has to go longer distance. We'll arrive at a later and later time. Okay, and one of the last slides, I'll talk about pump. Probe minus this slide that I've taken from Ziek Shen's group on Stanford. It's just from Stanford. It's a beautiful example. This is from the topological insulator bismuth 2 tellurium 3. Here is K. Here's energy, and then it's versus time, the pump probe time delay. If I can stop it at the right time, let me see. Maybe I can't. Okay, I can't. Right before 0, you can see, everything is just occupied. And once the pump photon comes in, there's all of a sudden all these states occupied up here, these unoccupied states. It's one of the really beautiful things about pump probe ARPES. You can access these unoccupied states because you're internally pumping them with that pump pulse. What they were focusing on here were the coherent phonons. In other words, you can see this band here oscillating up and down in energy with time. So there's some time dynamics to this thing, and they claim it's a phonon, a coherent phonon, and they're able to determine that by Fourier transforming this, measuring in time, finding the frequency of that, comparing to the frequency of phonons that they know are in the solid. Then there are stories, well, how are you connecting this coherent phonon? What is happening in the electronic structure to make this oscillate? So it's beautiful stories on this. I would say for this kind of hasn't worked so beautifully in correlated electrons yet. Usually the dynamics are so much faster that you don't see much. You excite things and electrons are down immediately, not so long-lived like this that you can really study these oscillations. And it should be obvious, but this is picoseconds. You need some sub-picosecond time resolution to be able to do this. In this case, I believe it's an optical phonon in this case. So if it's optical, it barely, it's pretty much K independent.
So it can be large K.
Yeah.
Couple.
So, then what people are doing here, then they'll do X-ray diffraction, time resolved also, and try to look at lattice dynamics and correlate these things. Is a really burgeoning field of people in this kind of thing. Okay, and not what I'm focusing on here, but for completeness, really wanted to mention this is where a lot of interest is. Okay, yeah, go ahead.
So what are these expressions? Are they only for electron bands or also other?
So this is electron dispersion. These are electron bands. It's E versus K of the electrons. This would be the Dirac point actually here. And so these normally would be totally inaccessible to ARPES, but because they're populating these electrons with this first pulse, the pump pulse, now they're accessible. It's like an electron heating effect. And now there's these hot electrons, but they need to decay. And in this compound, there's like a bottleneck for that decay. There's very few paths, and that's why you can see a lot of this stuff. Okay, yeah.
Excite the electrons beyond the frame.
Yes, you excite electrons from somewhere below to somewhere above. Yeah.
Two things. One is what is that blob below the Dirac point?
Valence band states. This is all valence band. The one thing I don't know what they're labeling, to me, the chemical potential should be here. I don't know why they call this 0. But
it's from something else.
I can just see it, right? When there's no, that's the edge of the states, and there's a here before the pump.
Second thing, can you say a few words just for the students about contrast between, doing synchrotron versus in the lab.
I will come to that.
You will talk.
I will come to that. Yeah. I'm sorry. Subir? It's just continuing, right? Right there. Yeah, that's where the Fermi energy is. And I don't know why they're calling this 0, but yeah. Okay. Let's see. Going way back, and in simplicity, just to the process of the photoelectron leaving the solid. Okay. There's a very famous model, 3-step model. This must be 1970s or something. I'm not sure. I should have it here. It was actually my PhD advisor. I should know this. But he thinks about the process, the photoemission process is 3 steps. First, there's the photoexcitation, and then this is not pump probe. Photoexcitation, photon comes in. Electron is excited up above the vacuum level. Remember, here's phi. That's the first step. Second step is, after that photoexcitation, this excited electron needs to transport to the surface before the third step, when it penetrates through the surface and escapes, and then we detect this thing. And here's the primaries, here's the secondaries. I already roughly showed that to you on this early slide. Now, this is just an approximation. It's what most of us think about. But the real quantum mechanical process, there's a 1-step model. And the entire process is quantum mechanical. And people know how to calculate. There's computer code using band structure calculations, et cetera, for calculating this. If you want to really understand the details, your matrix elements and whatnot, this is the best way to go. It's not really that illuminating, though. But it's good to know that this is what we think about. That's really not the full thing. So really, it should be one quantum mechanical process. Of course, there's also momentum conservation. That's not discussed in this 3-step model from Spicer. So we have photons, could be a few hundred eV or something. Whatever they are, they carry negligible momentum compared to the relevant momentum scale in the solid, of the electrons in the solid. Okay, so we need to think about this transition as a vertical transition in energy and k-space. So here's my vertical transition. And what's going to happen here? Where is the final state if I think of the simplest free electron picture? There isn't one. Okay, so this thing is forbidden. There's no final state. There's no photoemission process. So how does the photoemission happen? What saves us here? Well, we're not free electrons, but more specifically, I'm sorry, there's multiple bands, but why do we have those? Of course, it's because, the G vector. So there's all these bands, they're folded back, and so we need to go to one of those. Okay, so anyway, we of course need to use this extended zone scheme, employ the reciprocal lattice vector. The lattice degree of freedom really takes care of that missing momentum. Okay, and following up on the actual kinematics of the process, we go back to the late 70s. This was really worked out. It's extremely straightforward, just kinematics. Energy is h bar squared over k squared over 2m. We break into the parallel momentum components. I would say the only, and the angles, the emission angles, sine and cosine of theta. The maybe tricky thing is there's a term here we call the inner potential that affects the perpendicular component of the momentum. This we really don't have a first principle way to get it. So it really just becomes a fitting parameter. Usually it's not a big deal. At times it's a real pain in the ass for the experimentalist to find this, especially in sort of quasi two-dimensional materials. If it's fully three-dimensional, it's easy. If it's fully two-dimensional, we don't care about K perpendicular, and it's sort of the intermediate regime. And but I can just show you, okay, the point is, we can vary theta. We can do normal emission where that angle is 0. And in this paper, they spent a lot of time just varying, sitting at normal emission and varying the photon energy, which maps out K perpendicular. Okay. And here's the data. This is gallium arsenide. These are different photon energies, 25 eV, 30 eV, 40 eV to 100 eV. And there's all these, and everything is normal emission. Everything is theta equals 0. So the electron is just leaving the sample surface like this, but with different photon energies, which give different K perpendiculars. And they track the peaks. And here they track them, and they're comparing them to pseudopotential theory from a band calculation. And you see the really nice agreement of the experimental peaks is really setting the stage. People didn't believe that this would be possible. Here's another, this is basically the same set of data, tracking the peaks as they move and tracking the band through, a large range of kinetic energy. And here's this inner potential here that sort of is this offset of the very bottom first part of the band before it, this free electron final state band as it's moving up. Okay, and not really worthwhile going into any more details, but happy to talk about it. And the slides, of course, are going to be shared. Leonid, did you? No, okay. You had one.
So I'm just curious, how does the photon, like how do you like select the momentum position? Like
So in this case, it's just, we know K parallel is 0 because it was normal emission. Yeah. And measured the peak energies, so we know the binding energy. The only thing that was not really known was what is the true perpendicular. Do you fit it with many different inner potentials, is what we call many different of these values here. This is sort of the painful thing. It's in some respect a detail, but it doesn't really matter to case space. Yeah.
But K perpendicular is really the energy for you.
In
the end, that's
through, well, the energy has K parallel, perpendicular, has this offset if we want to convert to from P to K.
Right. I mean, there's all these offsets, but what I mean is the angular part, the angle of the K parallel that you see.
Mm-hmm.
Right. That's the.
So, and the next slide I'll show for 2D compounds. Normally we worry about K parallel. We ignore this K perpendicular or KZ dispersion. We don't need to vary the photon energies like was done here. There's other advantages as well, less final state broadening, et cetera, that I won't go into that. Here's the same kinematics. Now we're going to vary the angle. And we can track the peaks. And here's an example on strontium-2 ruthenium-04, strontium ruthenate. This is famous compound. It was for a long time believed to be spin triplet P-wave superconductor. This is the band structure now. Here's the measured peaks as a function of angle. And through 2 dimensions, here's, okay, so you're sitting at 1 photon energy, in this case 28 eV, and you're varying angle in all directions, theta and phi, and that's where the intensity is. And that's the calculated Fermi surface. Yes?
So fitting parameter is what you mean that for like a 3D material, you also have to do normal incidence first to calibrate?
Yep.
And then you, okay.
Yeah, yeah. And here we don't have to do that in principle. Now, really, this is still it's drawn in a plane. It's part of a sphere that usually is ignored. And if it's purely two-dimensional compound, we completely ignore it. Okay, and again, it's a quasi 2D compound where this can be painful. Okay, let me move forward. Surface sensitivity, I think almost everybody's heard ARPES has this. Here's a compilation from late 70s of many, many materials of the inelastic mean free path in nanometers of electrons through a solid. So remember, we have primary electrons and secondary electrons. The primaries are unscattered. This is how far they can go before they scatter and create secondaries versus the kinetic energy of these electrons. And a log scale. And the argument is, well, why does it turn around and have a minimum? First of all, the minimum is somewhere sub-nanometer typically, scatter depending upon the material, but nominally universal. And so this is, by the experimentalists, often termed just the universal curve. Okay, and at very high kinetic energy, any scattering process, there's decreased interaction times. Whereas here, there's decreasing phase space for the excitations off of plasmons, what have you. Okay, and so it's these two things crossing, giving a minimum, and that's really what gives the surface sensitivity. And that can, again, can be an advantage or a disadvantage. You can tune this somewhat by varying the kinetic energy of the electrons. You should do by varying the photon energy that you kick them out with. And let's see. Question, what do these instruments look like? How big are they? And Leo had also asked about synchrotron versus lab-based. So most of us doing ARPES travel to synchrotrons around the world. Here's a picture of two of the really nice facilities in the US at Stanford Synchrotron Radiation Lab at the Advanced Light Source Berkeley. This is a ring-shaped thing, so there's some relativistic, there's some ring that is 100-meter or something circumference, depends upon the facility. Electrons run around this thing at relativistic speeds, a few GeV typically. And whenever they bend around the corner, they emit synchrotron radiation. Synchrotron radiation is basically white light. If you put a monochromator with gratings in them, you can select out the photon energy you want, and you send it to your analyzer. There's a picture of the lens that we had before. Okay, and it looks something like this with your hemisphere here compared to people, your hemisphere here, etc. Okay. These things are great partly because you can very easily vary the energy of the photon by rotating these gratings and selecting the groove density, etc. They're not great if you want time resolution. Yeah. Yes. Yes. It's a little bit above that. It's typically, some 20, 30 EV. So maybe they're 10-ish. There's many things that electron can scatter off of, and that's certainly, part of it. Okay. We do the experiments in ultra-high vacuum chambers, typically 10-11 torr. There's 760 torr in an atmosphere, but that's partly because mostly we want to keep the samples clean because it's surface sensitive. We'll typically cleave or prepare the surfaces somehow in the ultra-high vacuum. So it makes the instruments big and complicated. And the other thing is that typical space where these experiments are carried out, most often in this 20 to 100 EV range. Those of us doing laser ARPES are walking up this curve. There's advantages to that. With hard X-rays, you can walk up this way, and there's a lot of efforts both sides with varying advantages and disadvantages for each. Just as a quick advertisement for the instrument upstairs, with the laser ARPES, this doesn't look great. Same material, same temperature, just compared to what we could do with the synchrotron at the time. And the spectral resolution is much nicer, much sharper. And here's the picture of the thing upstairs. Happy to take people on tours. Okay. One disadvantage of going with a laser, the K-space range is much smaller, again, just through the kinematics. The largest angle you can go to is 90 degrees. And so you don't have much K-space available. You cannot reach the edge of the zone for most samples. But if you're able to reach it, then it tends to work very, very nicely with very high energy and momentum resolution. Okay, questions at all? Yeah. I'm sorry, say that again. Usually not ionizing it, but I mean, I guess in a way you are. You're kicking the electrons out. You leave ions, positive ions behind. You need to replenish those electrons. So the sample needs to be connected to the ground. So you send the electrons back. Yeah, and if you don't do that, then immediately you're in trouble. My first impression of what you're talking about is you can also damage the sample. Certain samples are going to be, especially like organics, things with relatively weak bonds, will experience damage from the photons. While you're measuring, gas is also going to be landing on the sample surface and dirtying the surface. And because it's surface sensitive, your measurement is going to be changing, degrading. And it's one of the sad things about this spectroscopy. If you made one cleave and measured everything you possibly could imagine, you'd be done. And that is not the way life is for this spectroscopy. We have to redo many, many times and figure out what was a real effect, what was an aging effect, et cetera. Okay. Matrix elements. So this is Fermi's golden rule, initial state and final state. With your interaction, typically we just think about a dipole allowed transition. This gives various selection rules based upon the symmetry of the states that can be quite useful for selecting, for example, what are the orbitals that make up the initial state. So for example, I'm showing a dx squared minus y squared orbital coming in with a photon along this mirror plane that for my sample, if I'm trying to excite that state into a final state that is an electron plane wave, and the plane wave is going to be even symmetry with respect to that particular mirror plane. Yeah, to the mirror plane. But my initial state here, in this particular case, is also even with respect to that mirror plane that I've drawn in. Okay, and so let's see, the initial state was even or plus. The final state is plus. I can only excite that state out if my dipole operator is also even. Okay. In other words, for example, with a p-polarized light that has even symmetry with respect to that mirror plane. If I came in with an s-polarized photon, I'm not going to excite that state at all. Okay, because I'm going to integrate. What this means is I integrate across this. If the thing is odd, it integrates. That makes the sum integrates to 0 across that mirror plane. If I want to excite it with the other symmetry of light, well, I can rotate by 45 degrees, and now that state is odd with respect to that mirror plane. Okay, and of course, in calculations, especially these single-step calculations, they can do this in great detail and really show you across the zone. They're not perfect, but they can be helpful for fingerprinting what states we are photoemitting. Okay, questions? And this works quite nicely.
Can you extend this by using circular polarized?
Yes, yes. And we would use right circular and left circular, or we access chiral states, etc. It's another way to access also the spin of the electron, the electron, if you don't have a spin resolving. But I'm not going to talk about the details of that. Yes. Yes. It's not as direct as the spin ARPES. Okay. Let's go to look at real data, band dispersions. If we're talking COOP rates, the first really useful data, I would say, was from Cliff Olson back in 1990. And he was sitting at 90K. He's looking along the node. I think everyone knows what that means, but you can see a peak that is moving as the emission angle is changed. And then eventually the peak disappears, so the peak dispersed. He's drawing the centroids of these peaks on the band diagram, the calculated bands. And you can see there's something like a factor of 2 flatter bands or less dispersive bands from his data than was calculated. Something like a factor of 2 mass enhancement. And we still roughly believe that number. Okay, and that's just peak tracking. Data's gotten much more pretty over the years, but you know, this was great work. This is at 90K, so this is in the normal state as we're tracking the dispersion. A little bit after that, I think a very important paper. This is a model insulating COOP rate, strontium-2, copper oxygen-2, chlorine-2. And again, walking along diagonal of the Brion zone, and here's the dispersion of the peaks. If you do a tight binding calculation, you get this, and if you track these peaks, you get this, which is now extremely different. But if you do a TJ model calculation, then it matches quite well. And here you, in this calculation, you predicted bandwidth, 2.2J. And this J is extracted from other experiments as well. So, I'm sorry, what's the question? Yeah, so there's different cuts through. This is, you can take many cuts through the data. Pi 0 would be here, or 1, 0 in this case. Yeah, this doesn't agree as perfectly, that's right. I am sure there are, of course, now people do T prime, J, etc. I am not sure sure that it's the T prime that does that. I don't know. Subir, do you know T prime fixes this offset here, this difference? Okay. But, you know, much better agreement than a typical band structure calculation. Okay. Let's see. COOP rates as a function of doping, of course, is critical. Here's a selection of many measured Fermi surfaces versus calculated Fermi surfaces for different dopings. Let's see, very heavily underdoped, optimal doped, too heavily overdoped, and just, again, tracking where the locus of the peaks are, and then all put together in one place here. And so the underdoped to optimal doped has these Fermi surfaces around pi that everyone is familiar with. You dope hard enough, eventually you cross through and it looks electron-like. As you would expect, you can say that the Van Hove popped through the Fermi surface. And you had a transition. So again, you're just peak tracking, looking at the locus of these states. I would say one of the interesting things though, the peaks also, if I go from overdoped to more and more underdoped, they get broader and broader. These are self-energy effects, presumably, that make the peaks incredibly broad. And even tracking a peak here is, of course, quite difficult. And one of the things we're going to be working to try to do is really understand not just where the peaks go, but why they're so broad. And here's another important example from the literature. Another of these parent compounds, calcium oxygen chloride. And again, as you go underdoped, the peaks get broader and broader. They have had a model for this as a bunch of Frank Condon broadened peaks. So many different individual peaks, if you like, with one single quasi-particle peak at the top. There's some strange things like this supposed sharp peak. We really would expect it to have a varying dispersion as we varied the weight of that peak, or what we might think as the quasi-particle residue. The dispersion doesn't change. And that's still a mystery, I would say. Okay. I want to move back a little more modern data now. I've already shown you this slide, really trying to access these self-energies. We're using two-dimensional detectors now in one shot. Basically, you can get omega versus K, can track the peaks, can take cuts now at a constant momentum. We're termed momentum distribution curves. There's a peak. This is typically Lorentzian, or at a constant energy. Here's energy at K equals KF. These are typically not Lorentzian because there's energy-dependent self-energies. Although to zeroth order, of course, the width of this peak, delta E, should be related to delta K by multiplying by the velocity dE dk. Okay, and because these are Lorentzians, we often will fit these instead of trying to fit these. These from the same work are also going to be strongly temperature dependent. And I'm sorry, this isn't coming through so well, but this is some 40-something Kelvin, 80K, 300K, as there's temperature broadening of these momentum distribution curves. So this is K. This is cutting across this peak here, and then we're warming the temperature. I think a really nice step moving forward was worrying about the causality effects, the sigma prime and sigma double prime, the real and imaginary parts of the self-energy, which are measured independently. So the spectral widths as we, okay, so the red, the color is the experimental data. This is again on a cuprate superconductor, so energy versus K. Here's the Fermi edge. You track these peaks and you can plot a width or a sigma double prime. That's in red. They've symmetrized it around omega. And you can also plot sigma prime, remember, is the band renormalization, is the difference between the peak and your bare band, what you would have in the absence of a self-energy effect. Now, they don't really know the bare band, but they claim through a self-consistency they can access what that bare band would be. They have guessed that it's a parabolic band, but regardless, so there's a larger and larger sigma prime as you go deeper, and then eventually coming back as this thing would cross through and changing sign. Sigma prime should be odd, sigma prime should be even, as shown here. And what they claim is you take one of them, say sigma prime in blue, and you can get the equivalent thing by doing a KK of sigma double prime. So you measured the sigma double prime, you KK it, and you get the purple, and it almost matches. You can go the other way, and you can start with the measured sigma double prime in squares, and you can get a KK. You can take the KK of the blue one and you go back and forth and you do this iteratively until you access what the true bare band should be. Okay, the other option, of course, is you try to get the bare band just from a density functional calculation, and turns out it's also quite good. There are uncertainties in that, what density functional theory you're going to use, but it's quite close. So this is one of the really nice things. You're getting sort of independently both sigma prime and sigma double prime. They are both connected. Now, life isn't perfect. When you're doing the KK, you need to worry about what happens at very high energies. You're doing the integration over infinite energy, plus and minus. They're assuming that there's electron hole symmetry here in this. You need to model a little bit what's happening at the far edges, but those are sort of second order effects because the physics of the KK, you're dominated by what is happening at your own energy. Yes, you.
Measured with DC versus, what's caused by the apparatus versus what.
Yeah. So there's experimental energy resolution as well. You can usually get a pretty good handle on that, say measuring a Fermi edge of a known metal of gold, something like that. You can deconvolve the temperature broadening of that. Measuring the momentum resolution is a little harder. You also need to know that. But yeah, these are details that the experimentalists we will discuss in detail. But it's a great point. Yes.
Imagining one to get at least over the full band.
Yes.
I know this data is old, but nowadays people do this, do they at least cover the whole band when they do this self-consistent approach?
So as best as we can. So, why did they stop here? Well, usually the thing is getting so broad and you're not able to track it much farther. They tracked it as far as they could. And a lot of that broadening, is intrinsic. If this picture is right, it really is intrinsic and it's dying off. It's one of the uncertainties that, any real experiment has issues like this. The same exact thing, of course, goes with the optics. Yeah, but great question. Go ahead.
Some products are interested in the sound.
So I would say what tends to be most powerful, and I'll show some fitting the widest range of data possible, sort of simultaneously, many temperatures, many energies simultaneously, it gives us more constraints. I think if we went pixel by pixel, it's sort of fewer constraints. But people are looking towards machine learning. I would say in a few cases it seems to, but typically not so much yet. Yeah.
So as you heat this thing up, you start seeing this thing going above the Fermi level?
Tiny bit of it goes above, yes. And the peaks broaden, etc. And I will show effects of that. Yes. Okay. There's been a lot of interest in dispersion anomalies and kinks. Many of you, I think almost everybody has probably studied Ashcroft and Merman. This is a picture from within his book, their book. So a dispersive band and very near the Fermi energy within omega Debye. Here he's thinking of electron-phonon coupling. There is a renormalization of the measured band relative to the bare band in a low energy scale within omega Debye. So there's been a lot of interest seeing we can really learn about those processes. I think this was one of the first really clear cases. This was on a molybdenum surface state, so a metal. Here's the raw data. Doesn't really look so clean, but if you fit it, they claim they measure the dispersion like this compared to the bare dispersion. So again, there's some That's some renormalization effect. Band renormalization. The difference there is this real part of the self-energy, sigma prime, is plotted. So this is similar to what I showed before. Again, also plotting sigma imaginary part, sigma double prime. They're saying this part is electron-electron scattering, this part of the kink, this is coupling to phonons, but there's still some offset. Sigma double prime does not go to 0. So impurities, finite resolution, etc. Again, we're looking at sigma double prime and sigma prime together. One of the points here, though, is that sigma prime really is peaking at a specific energy that, again, they're saying is due to coupling to phonons with that energy scale. And there's been a lot of efforts in the cuprates and in other materials now looking for kinks in the dispersion due to this effect, the sigma prime or real part of the self-energy. There's been, it's typically in the superconducting state, but along the node where there's no superconducting gap, that's where the other scattering rates are suppressed. These effects come in. It's typically around 70 millivolts. I would say still not completely resolved what the origin is. Most common explanation is coupling to a boson, maybe a phonon, maybe the 41 millivolt magnetic resonance mode. There's still debates about this, but a lot of interest. Leo, you wanted to?
I was just wondering, variation of that energy with, I don't know, doping.
A little bit,
anything?
not dramatic.
What about-
And so for example, these are many materials and different dopings, and their claim is it's not varying much.
Way would look another direction.
In some respect, it gets stronger, but it's more complicated. And there's most of the effort has been this way. I think most of us believe there's definitely other physics going as we move towards where the pairing is really coming into play, and that's dominating something like this. Okay, I wanted to try to move to discussion of the strange metal state. So this is higher temperature above the superconducting TC and above the T star as well. And I know there's been discussions about that. Again, BISCO, this is normal state BISCO. So this is just above TC. This is a cut along the nodal direction. Do you have gaps are largest here, 0 here. So here's one of the plots that you've been seeing before, but turned on its side, energy versus K. What's done here, you take many cuts like this, and here are your MDCs. You can look at the widths of these MDCs versus energy, and it's looking something like this. Okay, so how do we describe the energy dependence of this? Let's see. Yeah, what might we think of? I guess I already flashed up a little bit. Maybe it looks sort of linear here. Maybe omega squared growing to linear. That would sort of be the natural thing. And so maybe at low frequencies, it's looking omega squared, forming liquid-like maybe, growing to something, some strange metal at higher frequencies. So that might be the natural thing. And when we took this data, that was, of course, what everyone was saying. We would argue this is not the case. And that this is really important for understanding the strange metal physics, nominally T-linear, omega-linear physics that has been discussed many times through these last 3 weeks. What I'll be trying to tell you is that we should really think about this not just as T-linear, but a varying exponent alpha. that deviates from linear and runs. So this alpha is going to run as a function of doping. And we wrote this down as an ansatz, okay, for describing this temperature and omega dependent scattering rate. So omega and T both come in quadratically. That's sort of the simplest way to connect both of them. And together they're raised to this power law, okay? If the power law is 1, then that's of course Fermi liquid theory. That's T squared or omega squared. If the power law is 0.5, which we argue is going to be basically for the optimal dose sample, it's either T linear or omega linear. And what's done here is there's many of these curves, but now at many different temperatures. So this is one temperature. I think that is the case here, probably. And you remeasure this at many different temperatures increasing. And so the spectra broaden as you raise temperature, broaden as you vary the energy. And now for different dopings, underdoped, heavily underdoped, out here, to medium, to optimal doped. Optimal doped and overdoped. And let's see, the other things in this equation, there's some coupling parameter to the self-energy, sigma double prime, is going to couple to this. And there's a term down here that's to keep this always unitless. Okay, as alpha runs, now this basically is just an energy term for any alpha. And it's expected that beta should be pi. We let it run. We let it vary as we did the fits. And any one set, all spectra and all energies at all temperatures and energies were fit simultaneously to this equation. And again, here's the results. So we found that this beta does roughly converge to pi for all dopings. Lambda is doping independent, was a nice finding, and that this exponent, alpha, is linearly running. It extrapolates up to 1, what you would expect for a Fermi liquid at high doping, like around 0.3 something, is 0.5 at optimal doping, and then goes sublinear below that. And I should point out that this term here was one value fixed at 0.5 UV, about the band bottom. Okay.
Is alpha angle dependent?
Okay, so this is along the node. Moving off of the node this has not been done carefully. We are in the process of trying to do that. But the first order response is, it seems like no. It seems it is not angle dependent. The overall scattering rate is increasing as we go off node. We don't understand why. But that is consistent across, if you look through all sets of data from other groups, et cetera. Okay. After publishing that, now a few years later, Mark Golden's group from Amsterdam measured different materials, so single layer Bisco rather than double layer Bisco, used the exact same formulation. Now these samples naturally are more overdoped, and those data points are his red circles, and they're here versus the samples from our case were these, and it basically follows along the exact same line. It was almost like a predictive thing for this, and lambdas and betas, they all came to roughly the same values. So this is something that is similar to the strange metal that we have heard about. It's T-linear. The claim here is that we should think about a smooth evolution, really. Not just T-linear, maybe with a fan. Let me go to, for example, the many phase diagrams where we have all this strange metal physics or T-linear behavior above, 1 quantum critical point or something. What this data is looking like is, well, there's, you know, everything is strange and everything is varying. As long as we're above this T-star line. So it's maybe something more like this. Doesn't look like there's a quantum critical point. If you like, everything here is looking critical. And let me back up a little bit about that. Here is scaling of the sigma double prime, these widths that we're fitting as a function of temperature and frequency. This is a parameter here. This is this combination, omega squared plus beta kt squared. And for the different dopings, and then the different temperatures all fall along this same line. So yeah, I think more and more theories now are starting to see these exponents that are varying. I know Subir has a lot of recent work that's starting to show this. So we started talking in detail, really trying to understand this, call it strange mental state, but we would call it, you know, more of a running. And these are the states that it's extreme broadening. And these are the states, of course, that once we cool down through TC, et cetera, they are the ones that make the superconductivity. Yes?
Is there any chance these experiments with the magnetic field at lower temperature, or is that
Okay, so yeah, of course, transport. That's been one of the ways to get down to zero temperature, to get inside the dome. ARPES in a magnetic field is a challenge. The electrons get carried off to weird angles. There are possibilities now with weak magnetic fields confined very near the sample. You can still do ARPES, but they're quite weak. So not nearly the regime that's needed to kill superconductivity. Yeah, no one.
thought of doing this like in the few samples that show something that looks linear above the like above the left overdose?
Yeah.
Is there any thought of doing such experiments?
I guess the most overdoped ones, you don't even have to worry about superconductivity. So the ones out here from the golden group, yeah, they're actually past the dome.
But they all did it at high temperature.
Here they can go to lower temperature because the dome is much lower. That's right. Yeah. Go ahead.
I would like to see that the value saturates at 1 for, you know, super heavily overdosed.
That would be beautiful, yes. We don't have such samples. Yeah.
Some regime alpha is low 0.5.
Mm-hmm. So below 0.5 would be a very interesting regime. And what should I say? Formally, the quasi-particle residue below 0.5 would be 0. And so that's a complete new type of electron gas, if you like. The residue is finite for this overdoped regime. And I can show you how this is calculated. There's actually 3 different ways to calculate the residue from the spectral function, and that's here. You basically look at the step in n of k. You can look at you know, d sigma prime d omega as that goes to 0, et cetera. So there's 3 different ways, and they're all consistent. Let's see. Questions? Okay. I would say this also connects nowadays. We can calculate optics experiments. So this is calculating the Drude conductivity versus experiment at the same temperature without adjusting parameters or adjusting the values. Agreement is quite good. The transport also can be calculated and connected. And this is something we're working much harder on now. And it really looks like even the phase diagrams, most of which came from resistivity, do need to be redrawn based upon the connection between the transport and the ARPES. Let's see. Okay, on to superconductivity in the last 15 minutes. Okay, so everybody's familiar with the dx squared minus y squared order parameter symmetry. ARPES is not phase sensitive, but still was very influential early on in determining that the superconducting gap, which can be observed by varying the temperature that you're measuring, is larger when you go towards the antinode, towards pi 0, and small at the node, and has this sort of characteristic V shape with the gap coming to 0 at the node. Okay, and of course, the phase-sensitive experiments, the Josephson junction experiments by Van Harlingen, Kirtley, et cetera, they really nailed this down, and it's really dx squared minus y squared symmetry. Trying to really measure the details of the self-energies and gaps at this antinodal regime has been of interest for a long time. It's been complicated. So this is raw data. This is from Ziek Shen's group. Out towards the antinode. And if you want to do the standard peak tracking, you can, what we know, we can track with EDCs or MDCs. And if you do the two of them, you get very different results. You can imagine if you're trying to, yeah, it has to do with the peak widths, these intrinsic peak widths. If the peaks are true delta functions, there's no problem at all. We just pick the peaks off. But it's these intrinsic self-energies that make the peak tracking difficult. One thing I want to show you is an advance made by Haoshang Li. He's now at Hong Kong University of Science and Technology. And so he was able to develop a true two-dimensional fitting technique. He's fitting EDCs and MDCs simultaneously. Here's the ARPES data, and here's a fit to the data in the color scale. What goes into this are self-energies, sigma prime and sigma double prime, and the determination of a bare band, like what we saw earlier for this nodal data from Kordiuk. But now in the superconducting state at the antinode. And the main thing he's extracting, again, are these self-energies. And let me show you what they look like. And I can go into more details of what they are. But there's, again, a bare band is a little lighter. It's going to be renormalized to a flatter, heavier mass through sigma prime. Both at the deep energies and very near the Fermi energy. There's going to be a gap that's determined. And these are all causally related. So there's a fitting routine that's going to extract both of these, and they're strongly temperature dependent, especially as they go into the superconducting state. Okay, you could call a kink energy scale if you like, where sigma prime peaks. Here's your kink in the dispersion that you see. That is more dramatic than what is seen at the node. Okay, and this is done with the Nambu-Gorkov, and here's the Green's function. Phi is your field. It's your gap delta times the renormalization Z, which is related to the real part of the self-energy. And here's the Green's function. Here's the self-energy, again, is the imaginary part of the Green's function. Okay. This is a mid-zone cut. And so towards the antinode. And I'll show you the full range on the next slide, but with the same formalism is used for all cuts, all temperatures. Okay, and this is just an example Okay, and let's see, here is still one cut, the same cut that is mid-zone. Here's the cut superior. So the node and the antinode, the cut goes across like this. And those 2 points there are the 2 points there and there, or if you like, where this parabolic bare band crosses KF there, and there are those 2 points. Okay, so that red line is the cut. Again, the experimental data and the fit for many different temperatures from the superconducting state where there is strong kink effects, strong normalizations, and superconducting gaps to well above T, C, and T star, where everything is more broadened out. Okay, and the self-energies that give these functions are plotted here or here, sigma double prime and sigma prime. Again, you call that a kink effect, the peak here, and these are causally related. Okay, so, and maybe a thing to point out, the sigma double prime, even at 0 frequency, starts very large. It's the broadening here. As you get colder and colder, all that sigma double prime, the scattering rate out to near 0 as we go into the superconducting state, as the peaks get sharp, and it gaps out roughly to something near 2 delta. And then there's the peak effect as well in the real part. Here's K dependence, multiple cuts from the antinode in red to the node in blue. And here we're cutting across the antinode in a, not along the diagonal, but here to keep the things the same.
Sigma prime.
So that's what we would normally think gives a kink effect. The peak is where the difference in dispersion is the largest. And so that's the change in the dispersion, the kink, which becomes really dramatic as we go to the antinode.
Is that a property of superconductivity, or is that the normal state?
It's a dramatic effect here at the antinode in the superconducting state. As we go into the normal state, this kink goes away. So it's partly the pairing. There are arguments that I talked about before where people think it's also, there's electron phonon coupling, etc. Deconvolving is a debate.
But it's also is it just the effect of turning, opening up a gap, and so now it's deviating a lot?
But okay, it's a very special gap, if you like. Opening a gap doesn't necessarily relate so dramatically. So it's really a change of the self-energy terms.
But before it was piercing, now it's turning over like in a bubble of dispersion. So now it's that
This is more than that.
It's not,
This is more than that. And you can see from the kink effects, etc. So the bogey above would just have the dispersion
I
come back.
Re-entrant thing.
That's right. That's right.
It's like S shape.
Yeah, exactly. Call that, or here in the experimental data. So that's where sigma prime is peaking. Okay, and just to point out this bare band as a function of temperature turns out to be temperature independent, as it should, as you would expect it should. That was not enforced in the analysis and the fits. It's something that made us more confident that that is a correct sigma prime. Okay, and correct bare band. So here's sort of putting it together. We can look at the weights here of sigma double prime, how they're varying. The weights of sigma prime is varying dramatically as a function of K, as a function of temperature. So the next slide, we're actually going to look at this weight, sigma double prime, that is dramatically varying as a function of temperature, and sigma prime at the peak, how it's varying as a function of temperature. and that's here. So this is sigma double prime at EF versus temperature, and it's decreasing with temperature and then starts to dive and head towards zero. Sigma prime, the peak, starts small at high energy and rises up dramatically. At high temperature, it rises up, whereas sigma double prime does the opposite. And we can track where these things happen in temperature. Here's where TC is. And there's really a change here at a slightly higher temperature. That temperature we're associating with the onset of pairing. So this is sort of a pre-pairing state. And there's a very strong evolution of the self energies at the start of the pairing and continuing through TC. Okay, and we have some story how this is all consistent. You start gapping out the low energy incoherent scattering. You create, here's the gapping. You gap out here, you create the peak here in sigma double prime, but through Kramers-Kronig, that creates the peak in sigma prime. And that peak in sigma prime, actually, if you like, is really what gives these super flat bands at the Fermi energy, if you like this reentrance behavior that Leo talked about. And that really increases the K range for the pairing well beyond what you would have without all these interactions. We argue that they actually give a positive feedback loop for helping to stabilize pairing, regardless of what the pairing mechanism is. And happy to talk about that more, but I know my time is quite tight. Let me see. The last thing I really had was coming back to a pump probe thing with quite beautiful work where they were measuring with X-rays and ARPES. But I guess I will skip that and stay here as my time I see is up. I'm happy to continue taking questions.
Question?
Yeah. So it's the line widths, which are sigma double prime, and it's the D, the bare band, which is sigma prime. And we are getting both of them in the spectra from the variation of the widths, broad peaks in energy and K, and sharp peaks. That is the sigma double prime. That's plotted here, extracted from the data. And then the deviation from the bare band was extracted from the data, but is reasonable based upon what you expect from DFT, et cetera. And so any of the deviations of the data from there is a sigma prime. And nowadays we're able to do self-consistent, causally self-consistent by enforcing Kramers-Kronig as well.
So the disorder doesn't affect the self-consistent.
Disorder. Okay, so that's a great question. I know it's something Subir is working super hard on now. There's disorder that we can think about just from impurities, say, that would, say, in a resistivity experiment, give you a finite residual resistivity. Here's temperature going to zero, and here is resistivity. Maybe it's near linear or something, but there's at zero temperature, there's some rho naught. We usually think about that from impurity disorder. That's a static effect. That's more elastic interactions, I think. And we certainly have that in ARPES. We would call that a gamma naught, a finite line width that would come at zero temperature and zero frequency.
Oh,
And let me jump way back here. That would be the gamma naught here for the different samples that we would argue is a impurity type of disorder effect. Now, I think nowadays, for example, a lot of what Subir is doing, Griffith's phases and things like this, there's disorder, but that's in the interactions themselves. And that is much richer. Yeah, this is, if you like, sort of a vegetable that you can subtract off. But it's the disorder and the interactions that I think many of us are pretty excited about now.
Question on here?
Now that you have the slide up again, how
Yes.
much you the MNR? Yes, we have like one separate machine. Sorry.
No, so this is fitting to a model form. And it's just one of the terms there.
Okay, so you also.
So there's, let's see, how many terms are there? There's, I want to argue that this term is essentially, it's fixed. They fixed it, we fixed it at the same value, 0.5 EV, chose it once. It sort of drops out anyway. If alpha is 0.5, say, is the sort of sweet spot, 2 times 0.5 is 1, minus 1 is to the 0, so this sort of drops out. There's a beta that, you know, is pi that sort of drops out, but it's a fitting parameter. There's alpha, there's lambda. So there's sort of 4 fitting parameters. 1, 2, 3, 4 fitting parameters and thousands of data points. So that's one of them that is self-consistently determined. Yeah.
How tight are the error bars on Python in this case?
So error bars are a great thing to discuss. In any experiment, there's statistics and systematics. And almost always the systematics are dominating. So for example, we get a sample and, you know, we can measure the TC. We need to put it on this curve somewhere to know does it fall on that line. And there's uncertainties there.
The value of alpha you get from these fits is like the little fit where well.
So the error bars as far as from those fits, I believe are smaller than the data points. And that's why neither we nor these guys bothered putting in error bars. They're smaller than that. I think the biggest thing is probably the doping uncertain, which is a systematic error. Yeah. Yeah.
How can, are you so another technique like yields, for example? Be an elastic version.
Right. First of all, the EELS is measuring dielectric response. There's a momentum transfer. So it's more like, yeah, it's a scattering event. It's more like a neutron scattering or something like that in a way versus measuring the individual K of the electron. So then you need some model to connect what is determining that scattering event, that momentum transfer. So Peter Abamonte at Illinois he's really pushing the back on this.
You guys are both looking at strange.
Yes, yes,
Interesting to know.
yes. So okay, then there becomes a lot of details. There's strong efforts, there's great interest, and I don't know if I want to really say much more than that at this point. I think it's a little early. And maybe a thing to say, even things that we thought were quite well sounded in this field for strange metals are no longer so much so. Let's say these phase diagrams, the boundaries are very subtle. And so the techniques that people have chosen, when is there a break, when is there a crossover, I think is one reason that you can look at so many different phase diagrams. They're all, and so it's something we're working quite hard on. I think we're very excited where that's going, sort of more hands-off ways to determine these boundaries. And I would say they're starting to really look like this rather than what you've seen.
So with
Okay.
this, let's just thank Dan again and come down and.
All right.
I'll buy their t-shirt, so come